Hello and welcome to Math Zone African Motives. Today, we're diving into the fascinating world of thermodynamics of gases. By the end of this tutorial, you will have a solid understanding of several key concepts that form the foundation of thermodynamics. Specifically, our learning objectives are to define and identify thermodynamic systems, understand the first law of thermodynamics and its sign conventions, master the gas laws, and solve problems involving heat capacity. Let's get started. First, let's establish our foundational concepts, beginning with thermodynamic systems. A thermodynamic system and its surroundings are part of the vast physical space we live in. We often define a specific boundary to study them. A system refers to a specific collection of matter, in our case, often a gas, or a defined region in space. Imagine a gas in a cylinder. That gas is our system. It's a precise quantity of matter we want to investigate. Next, the system boundary is the imaginary surface that clearly separates the system from everything else. In our cylinder example, the inner walls of the cylinder form the boundary. It can be any shape, and it's where the system interacts with its surroundings. And finally, the system's surroundings are everything outside the boundary. So, for our gas in a cylinder, the air outside, the table it sits on, even the earth itself, can be considered the surroundings. The boundary is the interface where the system and surroundings interact. Let's make these abstract ideas concrete with an example. This diagram shows an internal combustion engine. Here we can identify two distinct systems. First, we have a thermodynamic system. This is the combustion chamber above the piston. In this system, there's a fuel-air mixture. Both the matter, fuel, air, exhaust, and energy, heat from combustion, work pushing the piston, can cross this boundary. Second, we have a mechanical system. This includes the piston, crankshaft, and connecting rod. For this system, mass does not cross the boundary. The solid parts remain. However, energy is transferred through mechanical work to turn the crankshaft. Both systems have their own boundaries and are surrounded by the engine block and the outside air, which serve as their surroundings. Thermodynamic systems are further classified based on how they interact with their surroundings. There are three main types. First is an open system. This system can exchange both matter and energy with its surroundings. Think of a pot of boiling water without a lid. Steam, which is matter, leaves the pot. Heat, which is energy, also escapes. This makes it an open system. Next is a closed system. This system can exchange energy, but not matter, with its surroundings. Now, imagine that same pot of boiling water, but this time it has a tightly sealed lid. Steam cannot escape, so matter is conserved. However, heat still radiates from the pot, transferring energy to the air. This is a closed system. Finally, we have an isolated system. This is an ideal system that cannot exchange either matter or energy with its surroundings. A perfect thermos flask is a good approximation of an isolated system. It's designed to prevent both the liquid inside, matter, and its temperature, energy, from changing significantly due to the outside environment. Let's focus on the open system, also known as a steady flow system. As a reminder, in an open system, both energy and mass can cross its boundaries. A classic engineering example is a steam turbine connected to a generator. Here's what's happening. Hot steam enters the turbine, mass in, energy in. As it expands, it pushes on blades, causing the turbine shaft to rotate, work out. The cooler, lower-pressure steam then exits, mass out. There's also some heat that escapes from the turbine casing, heat out. Notice all these exchanges with the surroundings? Mass is flowing through, and energy is being converted. This is a perfect example of an open system. The key characteristics are that fluid or mass enters and leaves, and energy is transferred both into and out of the system in the forms of work and heat. Now, let's work through an example to see these principles in action. Here's the problem. Take a moment to read it. This problem is an energy balance for an open system. Let's list what we know. We have the energy supplied by the steam, the power produced by the shaft, and the heat loss. We need to find the power of the exhaust steam. The fundamental principle we'll use is the conservation of energy for an open system. In simple terms, all the power that goes into the system must either come out as work, come out as heat, or leave with the outgoing matter. We've identified our formula. Let's execute the plan. Our first step is to calculate the power of the shaft. This formula connects the rotational speed and torsion to the mechanical power. Be careful with units. We are given the speed N in revolutions per minute and the torsion T in kilonewton meters. We need to substitute the values carefully. In the solution provided, N is 3600 R min and T is 40 kNm. The conversion of 40 kNm to 40 times 10 cubed Newton meters is made for consistency with the formula. Calculating this gives us the shaft power. The result is 15.08 megawatts. This is the rate at which the turbine is doing work on the generator. Now we have all the pieces to apply our energy balance equation. The formula, as stated in the notes, is total power in equals shaft power out plus heat loss plus power in exhaust steam. Let's substitute our known values. We have 30 megawatts of energy supplied by the steam. This equals the 15.08 megawatts from the shaft plus the heat loss. But wait, the heat loss is given as 800 kilowatts, which is 0.8 megawatts. This is a very common place for mistakes. Always ensure all your units are consistent. So our equation becomes 30 equals 15.08 plus 0.8 plus the power in the exhaust steam. Now we just need to rearrange the equation to solve for our unknown. To find the exhaust steam power, we subtract the work and heat loss from the total input power. This gives us 1412 megawatts. So out of the 30 megawatts that entered with the steam, 1412 megawatts exit with the steam in the form of its internal energy. Let's check the book's solution. It matches our answer. This confirms our understanding of energy conservation in an open system. Next up, the closed system. While we briefly defined it before, let's explore it in more detail. A closed system allows for energy transfer, but matter cannot cross its boundary. An example is a gas inside a piston cylinder assembly. In this diagram, heat Q can flow in, changing the internal energy U of the gas inside, and the gas can expand, doing work W on the piston. However, the amount of gas, or mass, inside the cylinder remains constant. This is a non-flow system. The volume of a closed system can change, which has important implications for work. If the volume increases, like when a piston moves up, the gas inside does work on its surroundings. We will learn that this is considered negative work by the system. Conversely, if the volume decreases, the surroundings do work on the system, which is positive work. Our third type of system is the isolated system. An isolated system is an idealized system where there is no exchange of either mass or energy across its boundaries. As mentioned before, a very good thermos flask is a close approximation. A perfect isolated system doesn't truly exist because perfect insulation and sealing are impossible. However, this concept is incredibly useful in thermodynamics because we can often model a system as isolated over short time frames, or when the interactions with the surroundings are negligible. An even better approximation of an isolated system is the entire universe itself. According to the first law of thermodynamics, the total energy of the universe remains constant. That's as isolated as you can get. Now let's talk about the forms of energy that can be transferred in and out of a system. There are two primary types: heat and work. First, heat transfer, symbolized by Q. Heat is defined as energy transferred due to a temperature difference between two bodies. So, if you put a hot object in a colder room, heat will flow from the hot object to the colder room. There are three mechanisms for this transfer: convection, conduction, and radiation. Second is work transfer, symbolized by W. Work refers to energy transferred through mechanical means. For example, in our piston cylinder system, if the gas pushes the piston, it's doing work. If the piston is pushed down on the gas, work is being done on the gas. Finally, we have a property called internal energy, U. Internal energy is the total energy stored within the system. It's the sum of all the kinetic and potential energies of the molecules. It's important to understand the difference. Heat and work are forms of energy transfer. Like rain falling on a lake, internal energy is a property of the system, like the water level in the lake. You can change the lake's water level, U, by adding rain, Q, or letting water out of a dam, batata, W. These concepts bring us to the fundamental laws of thermodynamics. We will focus on the first and second laws. The first law of thermodynamics is one of the most important principles in science and is often called the law of conservation of energy. It states that energy cannot be created or destroyed. It can only change forms or be transferred from one place to another. The total energy in the universe is constant. This means that if a system gains some energy, that energy must have come from somewhere, either from its surroundings as heat or work, or it was converted from some other form of energy within the system. For an ideal gas, its internal energy, U, depends only on its temperature. Therefore, if the temperature of an ideal gas increases, its internal energy must increase. The first law is expressed mathematically by Joule's law. The change in the internal energy of a system, dU, equals the net heat transfer into the system, Q, minus the net work done by the system, W. The equation du equals Q, W is simple, but its application depends crucially on the sign convention. Let's break this down. This table from your notes is essential for getting the signs right. Let's go through it carefully. The signs are always defined from the perspective of the system. For heat, Q, a positive value, means heat energy is flowing into the system. A negative value means heat is flowing out of the system. For work, a positive value means the surroundings are doing work on the system. A negative value means the system is doing work on the surroundings. This sign convention is sometimes debated, but this is the one used in your material, so we will stick to it. For the change in internal energy, dU, a positive value indicates that the internal energy of the system has increased. A negative value indicates a decrease. This diagram also provides a visual aid for the sign convention. Notice that positive Q and positive W are arrows pointing into the system, while negative Q and negative W are arrows pointing out. This visual representation can be very helpful. Let's apply the first law to an example problem. Here's our problem. A system has 850 joules of heat energy added to it, and it does 220 joules of work on its environment. What is the change in the internal energy of the system? The first step is to identify the quantities given and determine their signs using the convention we just learned. We have 850 joules of heat energy added to the system. From our table, this means Q is positive, so Q equals plus 850 joules. The system does 220 joules of work on its environment. Again, from our table, this means W is negative, so W equals 220 joules. We are solving for dU, the change in internal energy. The diagram provided also visually confirms these signs. Notice the Q arrow pointing in and the W arrow pointing out, which matches our convention. Now we write down the first law equation. dU equals Q minus W. We have the equation and our signed values. Let's calculate the final answer. We substitute our values into the equation. dU equals plus 850 minus negative 220. Remember that subtracting a negative number is the same as adding a positive number. So our calculation becomes 850 plus 220. The change in internal energy is plus on 1070 joules. The positive sign tells us that the internal energy of the system has increased. However, the solution in your notes gives a different answer. Let's re-examine it. The notes solution uses dU equals Q minus W, which is correct. It substitutes 850 for Q and 220 for W, which implies it's using a different sign convention for work. Specifically, it seems to use W as positive when work is done by the system. But let's stick to the sign convention given in Table 1.1, which states that work done by the system on its surroundings is negative. Following the convention from Table 1.1 strictly, which is work done on the system is positive and work done by the system is negative, our calculation is correct. Therefore, the change in internal energy is 1070 joules. It is crucial in thermodynamics to always know and use a consistent sign convention. The one provided in your notes, where the system doing work means W is negative, is a common and recommended standard in engineering thermodynamics. So based on that, the change is 1070 joules, indicating the system gained internal energy. Let's tackle a more complex problem involving a two-step process. The problem states that a system goes through two processes. In the first, It gains 50 joules of heat and does 22 joules of work. In the second, it loses 30 joules of heat and has 5 joules of work done on it. The diagram visually confirms the inputs and outputs for both steps. Notice that Q1 and W1 correspond to the first process, and Q2 and W2 to the second. Because internal energy, U, is a state function, meaning it only depends on the initial and final states and not the path taken, we can find the total change by either summing the changes from each step or by finding the net heat and net work over the entire process. Let's try both methods. Let's first calculate the net heat transfer and net work for the entire two-step process. First, the total heat. In the first step, 50 joules are added, so Q1 is plus 50. In the second step, 30 joules go out, so Q2 is 30. The net heat transfer, Q, is their sum, which is 20 joules. Now for the total work. In the first step, the system does 22 joules of work, so W1 is 22. In the second step, 5 joules of work are done on the system, so W2 is plus 5. The net work, W, is their sum, which is 17 joules. Now we have the net Q and W for the entire process. We can use the first law to find the total change in internal energy. The change in internal energy, dU, is the net heat minus the net work. Substituting our values, we get 20 minus negative sin, which equals 37 joules. The positive sign means the system gained 37 joules of internal energy. Let's confirm our answer by doing it the second way, which is to calculate the change in internal energy for each process individually and then add them up. For the first process, Q1 is plus 50 sal and W1 is 22. Using du1 equals Q1 minus W1, we get 50 minus negative 22, which is 72 joules. For the second process, Q2 is 30 and W2 is plus 5. Using du2 equals Q2 minus W2, we get negative 30 minus 5, which is negative 35 joules. Now, we add these individual changes to get the total change. The total change in internal energy is 72 plus negative 35, which is 37 joules. This matches the result from our first method. Now let's compare with the solution in the book. The notes also use two methods, but the calculations are different. This indicates another inconsistency in the provided solution. It appears the notes might be using a different sign convention for work or have an arithmetic error in the second method. Let's verify our own answer. The initial question asks for the total change in internal energy over both processes. Internal energy is a state property, so the total change is the sum of the changes in each process. The first law states U equals Q, W. Using the sign convention that work done by the system is negative, our calculation is correct. Therefore, the change in internal energy is plus 37 joules. Again, this highlights the importance of using a consistent sign convention in thermodynamics. We now move to the second law of thermodynamics, also known as Clausius's law. This law tells us something very important, the direction of a process. The second law identifies the direction of a process. Heat energy can spontaneously only transfer from a hot body to a colder body. It cannot naturally go from a colder body to a hotter body. Think about it. If you put a cold ice cube in a warm drink, the ice cube melts as it absorbs heat from the drink. The drink gets colder. You never see the drink get hotter and the ice cube grow larger spontaneously. That would be a violation of the second law. This diagram perfectly illustrates the law. Heat transfer from hot to cold is a natural process indicated by the check mark. Heat transfer from cold to hot is not spontaneous, indicated by the X. This simple law has profound consequences. It explains why heat engines can never be 100% efficient and why perpetual motion machines are impossible. It places a fundamental limit on how much useful work can be extracted from heat. To help quantify the direction of processes, Clausius introduced the concept of entropy. Entropy, symbolized by S, is a measure of a system's heat energy per unit temperature that is unavailable for doing work. It's often described as a measure of disorder or randomness within a system. The Clausius form of the second law can be stated in terms of entropy. It says that for any spontaneous, irreversible process in an isolated system, the entropy of the system will always increase. This means that the total disorder of the universe is constantly increasing. This is a powerful concept that helps explain why certain processes happen in one direction but not the other. For a simple transfer of heat at a constant temperature, the change in entropy, delta S, is calculated as the heat transferred, Q, divided by the temperature, T. For a heat engine operating between two temperatures, T1 and T2, the change in entropy of the engine and its surroundings is given by this second equation, which takes into account the heat absorbed from the hot reservoir and rejected to the cold reservoir. For any real process, this total change in entropy must be positive. To make accurate comparisons of gas properties, scientists and engineers need standard reference points. This is where standard temperature and pressure, or STP, comes in. Because atmospheric temperature and pressure can vary wildly, we need a consistent benchmark. Standard temperature and pressure, or STP, refers to these nominal conditions at sea level. Standard temperature is based on the freezing point of water, which is 0 degrees Celsius, or 273.15 Kelvin. You'll notice we always use Kelvin in thermodynamic equations because it's an absolute temperature scale, where 0 Kelvin means 0 molecular motion. Standard pressure is 1 atmosphere, which is 101.325 kilopascals. It's important to be able to convert between Celsius and Kelvin. The formula is simply to add 273.15 to the Celsius value. For example, 0 degrees Celsius is 273.15 Kelvin. Another standard point is normal temperature and pressure, or NTP. The normal temperature is 20 degrees Celsius, or 293.15 Kelvin, and the pressure is the same 1 atmosphere, or 100.325 kilopascals, as STP. Our next topic is specific heat capacity, a crucial property when dealing with temperature changes. Specific heat capacity, C, is the amount of heat energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius or Kelvin. Its unit is joules per kilogram Kelvin. Its symbol is C. The value of C is constant for solids and liquids, but for gases, it's more complex. For gases, the specific heat capacity depends on the process used to transfer the heat. The formula that relates heat, mass, specific heat capacity, and temperature change is this. VQ is the heat added in joules, AM is the mass in kilograms. C is the specific heat capacity in joules per kilogram Kelvin, and dT is the change in temperature in Kelvin. This table shows the specific heat capacity for water in its 3 states. Notice that the value is very different for liquid water, ice, and steam. This is because the molecules in each state have different arrangements and ways of storing energy. Because the specific heat capacity of gases depends on the process, we need to consider 2 specific types: specific heat at constant volume, C sub V, and specific heat at constant pressure, C sub P. C sub gas. C sub V is the heat needed to raise the temperature of a gas by 1 degree while keeping its volume constant. Look at this diagram. We add heat Q sub V to a gas in a sealed, rigid container. The temperature and pressure increase, but the volume V stays the same. Since the volume doesn't change, the gas doesn't expand or contract, and therefore it does no work. So all the heat added goes directly into increasing the gas's internal energy. The formula is Q sub V equals M times C sub V times delta T. Now let's compare this to C sub P, the specific heat at constant pressure. C sub P is the heat needed to raise the temperature by 1 degree while keeping the pressure constant. See this diagram? We add heat Q sub P to a gas in a piston cylinder assembly. To keep the pressure from rising, the piston moves up, the volume expands, and the gas does work W on the surroundings. In this case, the heat we add not only increases the gas's internal energy, but it also provides the energy for the work done. So C sub P is always greater than C sub V for a gas. The formula here is Q sub P equals M times C sub P times delta T. Following our discussion of specific heat capacity at constant pressure, it's a good time to derive the work done during that process. We said that when heat is added to a gas at constant pressure, it expands and does work. The general formula for work is pressure times the change in volume. For a constant pressure process, it's simply P times the final volume V2 minus the initial volume V1. Using the ideal gas law, which we will introduce formally soon, we can find an alternative expression for work. The ideal gas law for an engineering system is PV equals mRT. Since the pressure P is constant, the work due equals mR times T2 minus T1. T2 and T1 are the final and initial temperatures in Kelvin. R is a constant specific to the gas, called the characteristic gas constant, and m is the mass. This gives us two convenient ways to calculate the work done at constant pressure, depending on whether we know the initial and final volumes or temperatures. We're almost ready to solve our next problem. First, let's have a quick recap of the four general gas laws. These laws describe how the fundamental properties of gases, pressure, volume, and temperature, are related. All of these laws apply to an ideal gas. An ideal gas is a model that simplifies the behavior of real gases, especially at low pressures and high temperatures. First, we have Boyle's law. It describes the relationship between pressure and volume. Boyle's law states that at constant temperature, the volume of a gas is inversely proportional to its pressure. This means if you increase the pressure on a gas while keeping it cool, its volume will shrink. This is shown by the decreasing curve on the graph. Next is Charles's law. It relates volume and temperature. Charles's law states that at constant pressure, the volume of a gas is directly proportional to its absolute temperature. So, if you heat a gas and keep the pressure steady, its volume will expand. This is shown by the straight upward line on the graph. Then we have Gay-Lussac's law, which connects pressure and temperature. Gay-Lussac's law states that at constant volume, the pressure of a gas is directly proportional to its absolute temperature. Imagine heating a can. The can's volume is fixed. As the temperature rises, the gas inside expands, hitting the walls more frequently and with more force, so the pressure increases. This is also a straight upward line on its graph. There are two more fundamental gas laws to cover. First, Avogadro's law. This law says that for the same volume of any gas at the same temperature and pressure, there is the same number of molecules or atoms. A key takeaway from this is that 1 mole of any ideal gas at STP occupies a volume of 22.4 liters. In other words, volume is directly proportional to the number of moles, N. Finally, the grand combination of these laws gives us the ideal gas law. The ideal gas law is a combination of Boyle's, Charles's, and Avogadro's laws. The notes present two forms: the standard form, PV equals nRT, and the engineering form, PV equals mRT. We will use the engineering form, which is more practical for many problems. The engineering form of the ideal gas law is PV equals mRT. Here, P is the pressure, V is the volume, M is the mass of the gas, R is the characteristic gas constant, and T is the temperature. This is a very powerful equation that relates these 5 important properties of an ideal gas. Now let's see how these laws come together in an example. This problem combines STP with the combined gas law. The problem asks for the new temperature of a gas when its pressure and volume change from STP conditions. Let's first list our initial and final states. State 1 is at STP. We know the pressure is 101.325 kilopascals and the temperature is 273.15 Kelvin. The initial volume is 800 milliliters. State 2 has a new pressure of 160 kilopascals and a new volume of 700 milliliters. We need to find the new temperature, T2. Since the mass of the gas in the cylinder remains constant, we can use the combined gas law, which is a rearrangement of the ideal gas law. P1V1 over T1 equals P2V2 over T2. Now we substitute all our values into this equation. The pressures are in kilopascals on both sides, so they will cancel out. The volumes are in milliliters, which are 10 to the power of -4 cubic meters. The temperatures must be in Kelvin. Our goal is to solve for T2. Let's simplify the equation. First, let's calculate the left side of the equation. 101,325 times 0.08, all divided by 273.155, gives us approximately 0.02967. The right side is 160 times 0.07 divided by T2. Now we can solve for T2 by cross-multiplication. T2 equals 11.2 divided by 0.2967. This gives us approximately 377.4 Kelvin. The problem asks for the answer in Celsius. To convert from Kelvin to Celsius, we subtract 273.15, so 377.4 minus 273.15 gives us 104.25 degrees Celsius. Let's check the solution in the notes. The notes solution correctly sets up the equation and gives the answer as 377.409 Kelvin and 104.259 degrees Celsius, which matches our result. Our calculation is correct. You see, the combined gas law is a very powerful tool. Final answer. The new temperature of the gas is 104.25 degrees Celsius. Notice how the temperature increased, which makes sense, as the pressure increased and the volume decreased, both contributing to a hotter gas. We've seen that C sub P is greater than C sub V. Let's now explore the important relationship between these two specific heats for an ideal gas. The difference between them is the characteristic gas constant, R. That is, C sub P minus C sub V equals R. Let's briefly understand why this relationship holds. The difference R represents the extra energy required at constant pressure. This extra energy isn't used to raise the temperature. It's used to do the work of expansion against the constant pressure. This work done on expansion is exactly what the characteristic gas constant R accounts for in the ideal gas law. The notes also provide a proof of this relationship. It uses the first law and the ideal gas law to show that R equals C sub P minus C sub V. The derivation, though interesting, confirms this fundamental equation. For a common gas like air, which we often approximate as an ideal gas, we can look up the values. C sub P for air is about 1.5 kilojoules per kilogram Kelvin, and C sub V is about 0.7107 kilojoules per kilogram Kelvin. Their difference gives us the characteristic gas constant for air, R, which is 0.288 kilojoules per kilogram Kelvin. This constant, R, is specific to air and is used in the engineering form of the ideal gas law. There's another very important ratio in thermodynamics, the heat capacity ratio, represented by the Greek letter gamma. Gamma is simply the ratio of C sub P to C sub V. It's a dimensionless quantity, meaning it has no units, and it's a thermodynamic property specific to a given ideal gas. Gamma, also known as the adiabatic or isentropic expansion factor, plays a critical role in describing how gases behave in processes where there's no heat exchange with the surroundings, like the compression in an engine cylinder just before ignition. Using the values for air, we can calculate its gamma. C sub P is 1.5 and C sub V is 0.717. Dividing them gives us a value of approximately 1.4 for air. This value of 1.4 is very common in many engineering calculations.